In this video we will take a look at the Electroweak theory, which unites the weak and electromagnetic force. This theory shows us how these two fundamental forces are linked and how they unite at high energies, forming the electroweak force. In the video about the weak force, we discussed how we couldn't just write down the Lagrangian for the weak force in the same way as we did with the electromagnetic force. The reason is that we are not allowed to have massive gauge bosons, or in other words, the force carriers must be massless. This is fine in QED in part because the photon is massless, but this doesn't work for the weak force, as the W-, W+, and C bosons are all massive. The answer to how these particles are allowed to be massive is explained by the Higgs mechanism, which is an essential part of the electroweak theory. Because these two forces only unite at energies above our everyday life, we don't experience this unification, but we can recreate the high energy conditions at the LHC at CERN. To understand the essence of the issue, we must understand that the standard model is based on gauge theories with certain symmetries that the theory must obey. The symmetry group of a standard model is a rather complicated topic that deserves a video on its own, but the essence is that when you write the Lagrangian of the standard model such that it obeys the underlying symmetries, then we are not allowed to write any mass terms for our gauge bosons. Thus, all our force carriers of the standard model must be massless. If we wrote mass terms, we would break the symmetry of the standard model, which means we break gauge invariance, and this just means that the standard model would be completely useless. The trick is that we can write the standard model Lagrangian such that it abides to the necessary symmetries, but we can write it such that it has a symmetry breaking mechanism. Thus, the Lagrangian abides to the necessary symmetry, but it has a mechanism to then break this symmetry, and this symmetry breaking is what generates the masses of the weak force bosons. This mechanism is called the Higgs mechanism. The development of the electroweak theory goes back to the 1960s, when scientists suspected that the weak force and the electromagnetic force were related. On top of that, they were also looking for a way to explain how the force carriers, the W-, W+, and the C bosons, could be massive without ruining everything. This led to a theory with four massless electroweak bosons called the W1, W2, W3, and B bosons. Initially, scientists proposed just to manually do a symmetry breaking which would turn three of the bosons massive. But that solution was no good and obviously not natural. The solution came from Peter Higgs, who had earlier proposed a new Higgs field, and this field would have a potential with a particular shape, and that potential would spontaneously break the necessary symmetries to get the correct massive gauge bosons or force carriers. You might think that the W1, W2 and W3 bosons become the weak bosons, and then the B boson becomes the photon after the symmetry breaking, but it's more complicated than this. What actually happens is that the W1 and W2 bosons mix to form the charged W- and W+ bosons, and likewise the W3 and B bosons mix to form the Z boson and the photon. But the photon remains massless, while the other particles will become massive. Let us now discuss in more detail how this potential works and how it results in these masses. To do this, we have to introduce something called the vacuum expectation value, or F. This is the average value of the vacuum of the Higgs field. We often write it just as V, and this is the only mass parameter in the standard model. Thus, any fundamental particle with mass is related to the value of the VEV. Thus, the actual value of the VEV has a direct impact on the masses of all massive particles of the standard model. The potential is like a parabola at energies above 160 GeV, but at colder temperatures corresponding to energies lower than 160 GeV, this potential changes into the famous Mexican hat potential. Let me just say that 161 GeV is incredibly hot and room temperature is many orders of magnitudes less than a GeV. Any physical system would like to minimize the energy, so the Higgs field drops into the new minima of the Mexican head potential. The key here is that the VEV of the Higgs field is the distance from the center to the Higgs field. In the parabolic potential, the Higgs field is at the origin, so the VEV is 0. But in the Mexican head potential, the Higgs field is now shifted away from the origin, and this displacement on the x-axis leads to the VEV becoming non-zero. The VEV actually has a value of 246 GeV. This change from the parabolic potential to the Mexican head potential is the spontaneous symmetry breaking, which leads to the mass of the weak bosons, and it gives mass to the Higgs field, which in turn gives mass to all the other fundamental particles. This symmetry breaking is called the Higgs mechanism. Before moving on to show you exactly how the masses appear, let us talk a bit more about symmetry breaking from the point of view of the symmetry groups. The group involved in the electromagnetic force is called U1, and this group has one so-called generator. What is important here is that generator equals bosons. Thus one generator means one boson. This is why the electromagnetic force has just one boson, namely the photon. The group involved in the weak force is called SU2, and it has 3 generators. This therefore means that we have 3 bosons associated with this force. To create the electroweak theory, we obviously must combine these 2 groups to form a combined theory. Thus the group of the electroweak theory is the product of the group of the weak and the electromagnetic force. This gives us the group SU2 cross U1. When we talk about symmetry breaking, in the case of the Higgs mechanism, we are talking about the breaking of the generators of the SU2 symmetry group. Because it has 3 generators and they all get broken by the Higgs mechanism, then we get 3 massive weak bosons. Thus a broken generator means a massive boson, and since the U1 group remains unbroken, then the photon stays massless. Now let us look at the math of the situation. The Lagrangian for the electroweak theory has many terms, but one term is instructive to show how the symmetry breaking works. This term is written before symmetry breaking as L is equal to d mu, phi and all that squared, where phi is the Higgs field and the d mu term is the covariant derivative of the SU2 cross U1 symmetry group. This term can be written as d mu is equal to a half and in parentheses 2 partial mu plus I g prime b mu plus I g sigma I w I mu. Here we just focus on the 2 last terms. We first note that the U1 gauge field is called b mu, which gives us the B boson of the unbroken electroweak theory. The coupling constant of this field is g prime. In the next term we have 3 W bosons, as the index I goes from 1 to 3, the coupling for the bosons is G. The sigma I term is the 3 generators of the SU2 group, which are all broken by the symmetry breaking. Now the last thing we will discuss is how symmetry breaking gives us mass terms. What we will do is to insert the value of the Higgs field after symmetry breaking into the Lagrangian presented in the previous slide. We write the Higgs field in the symmetry broken state as phi is equal to 1 over the square root 2, and then the upper value of the vector is 0 and the lower value is h, the Higgs field, plus v. And then we plug this into the Lagrangian. It is equal to d mu phi and that's squared. And then we do a lot of math and get a lot of terms, but we are interested in the masses. As discussed before, the W- and the W+ boson come from the W1 and W2 bosons. And these bosons have the same mass but just opposite charge, and we thus get the 2 terms, a half mw squared, parenthesis W mu1 squared plus W mu2 squared, where the mass of the weak force W bosons is MW equal to a half GV. And we can explicitly see here that the mass depends on the vacuum expectation value V and the coupling. Something similar happens for the C boson, but because of the mixing there's a bit more work to do to figure out the mass term. But this illustrates how we get the mass term from the Lagrangian. This video has focused on the electroweak theory and how it explains the mass generation of the weak bosons, namely the W-, W+, and the C boson. We also discussed the Higgs mechanism and how this symmetry breaking causes the Higgs field to become massive. The rest of the massive particles in the standard model get their masses from interacting with the Higgs field, but we will discuss that in the next video. This video was very technical, but I hope you learned something new. If you would like to see more videos, please support me using the link below. If you have questions or any other feedback, then put it in the comment sections below. As always, please like and subscribe. See you in the next video. Stay tuned.